emission cuvettes are going to look a lot like one of our normal cuvettes that we worked with in spectroscopy. And that's where we said that we would just have our normal square 1 centimeter cuvette with my great skills of an artist here. And we said that we'd have our, I'll just go like that, and we can even have a little dotted line there. There we are. Okay, so our normal square cuvettes. So nothing fancy where we had the cooling things built in, none of the flow through, none of those microliters, none of that. We're just going to stay with a normal cell. The thing is, when we work with a normal cuvette, we're going to have a frosted side on one side, a frosted side on the other side, and then the light goes through the polished sides. That way we hold it on the frosted sides without getting any messing up on the surface. Well, in emission cuvette, what we've actually done is we've polished off these sides as well. So all 4 sides of this are going to be totally transparent and well polished. The reason for that is that if our excitation beam is coming in, and you see here I'm showing a violet beam coming in, so high energy, they're going to photoexcite a bunch of these molecules. Each of these molecules are suddenly going to give off a photon whenever they're ready to. We've seen that from the Jablonski diagram. And that photon is going to go in a random direction. And so you can see that we're going to have them going in all kinds of different directions. Now this means that even if you have a perfect conversion, even if you have our quantum yield of fluorescence, of FL, equaling 1.00, for every single photon that's absorbed, it's going to give off a fluorescent photon. Not real likely, but we'll go for that assumption for a second. If we're under those conditions, at any spot where you're actually looking at it, you're not going to be seeing anything near as bright of a light as what you sent in there originally. And that's because all of this light was going in a straight line. So if we put our eye right here, we'd be seeing a really bright light coming into our eye. If I put my eye right here, not so much. Only a couple of photons are coming to it compared to all of these others that are being scattered. And keep in mind, too, that this diagram is in 2 dimensions. We're going to have things scattering above and below that plane. So you see that we're not going to have quite as much light coming to us. Why would we want to measure fluorescence off to the side then? Well, keep in mind that it's so bright coming forward that there's a good chance that a lot of that light is going to totally overwhelm the tiny bit of the green fluorescence that's going to come this direction. As opposed to coming this way, these cuvette faces are very well polished. We want to make sure there's no bubbles or turbidity of any sort in our cuvette. And if there isn't, since transparent, the light keeps going in this line. It doesn't get scattered to the side. So we see no violet light over here. So now I'm only looking at the green light. There may not be a lot of the green light, but it's pretty easy to see any green light against a completely black background, which is what you'd be observing from the side. And that's why we do the measurement at 90 degrees from the excitation beam path. There's just no background signal for us to have to worry about.